My name is Francisco Santiago Nieto de la Rosa, and I will present our work, Machine Learning Models on Antimicrobial Resistance Prediction. Antimicrobial resistance, or AMR, is a critical global health challenge, and predict antibiotic susceptibility based on genomic data is crucial in fighting AMR. This year, as part of CAM the Community Challenge, we aim to predict antibiotic susceptibility using bacterial genomic data. So, to start, let me introduce the data we use. We work with more than 7,700 isolates across 9 bacterial species. Each isolate has label indicating susceptibility and minimal inhibitory concentration, or MIC, for two antibiotics, meropenem and ciprofloxacin. Our primary goal was predict when an isolate is resistant or this antibiotic and at what concentration. So we start doing pre-processing of ascension to get tables. Given with high dimensional of genomic data, we did feature selection and dimensional reduction to produce data for training machine learning models, and this will give us the results. On one hand, with assembles and card database and algorithm, we did an AMR detection to get 4 AMR count tables, 2 for each antibiotic. On the other hand, we use Rust for annotation and get sets of genes, and with pangolin we did a pangenome for each antibiotic. Well, by the dimension of the pangenomic, we prefer focus on the AMR count tables. Also, our work requires efficient features selection and dimensional reduction techniques. So we focus on 3 main methods. Biological filter. Here we select genes associated with beta-lactamases for meropenem and efflux pumps for ciprofloxacin. Mutual information. This was machine learning methods. These methods involve calculating mutual information between features and targets and selecting the top 100 features. Game theory-based evaluation, using an approach inspired in Shaduri et al., we evaluate features based on relevance and importance using game theory. Each of these methods yields very different gen sets. This variation gave us a robust set of features to work with, as each method highlights different aspects of the data. Here you can see a Venn diagram illustrating overlap between the gen selection of each method. Another consideration is about unbalanced data. For example, more than 90% of the isolates of ciprofloxacin are labeled as susceptible, so that's a consideration. With this dataset, we trained several machine learning methods to predict the phenotype. For example, random forests, KNN, logistic regression as lasso, and this is the only method that we use to predict MIC. Gaussian eye bias, multi-layer perceptron, support vector machines, and XGBoost. These models were evaluated to determine the best model for predicting resistance for each antibiotic, and our results are summarized in this table. Performance varied across bacterial species, with some like Pseudomonas aeruginosa and Enterobacter cloacae showing the higher error rates. This indicates that resistant predictions can be more challenging for certain species, likely due to unique genetic factors or data imbalance. In addition to predict resistance, we also developed a model for MIC prediction. This aspect is still in progress, and we are exploring assembled models and neural networks to refine our predictions further. Other plans that we have includes integrating more advanced techniques like topologic data analysis, kernel PCA, and improved neural network architectures. We are also considering class weighting to address data imbalance issues. So to conclude, our study highlights the potential of machine learning in prediction antimicrobial resistance using genomic data. However, are still challenged, specifically with unbalanced datasets and complex bacterial species. Thank you for your attention, and I'm happy to answer your questions.